In this video, let's take care of the second part of exercise 2.3. Sketch the curve of y equals 4x squared plus 3x minus 1 divided by x plus 2. So this is a rational function. The degree of the numerator is 1 more than the degree of the denominator. So let's go ahead and do polynomial division to find if we have an oblique asymptote or not. Which we should, because it seems like x plus 2 is not a factor of 4x squared plus 3x minus 1. Okay, so 4x squared plus 8x minus 5x minus 1, so minus 5. Right, so that's our oblique asymptote. I'm just going to finish it off because of OCD or whatever. Minus 10, so 9. So that's our remainder. Okay, so our oblique asymptote is y equals 4x minus 5. Next we can check if the function, well, we've already proven earlier that this function can only intercept its oblique asymptote if it's not a simplified rational function, in which case the remainder would be 0. So we know that this particular rational function cannot intercept its oblique asymptote. Be careful, I don't mean that rational functions in general cannot intercept their oblique asymptote, but in the particular case of ax squared plus bx plus c divided by x plus d. This one here cannot intercept oblique asymptote. Okay, now it has a vertical asymptote at x equals -2. Next we can check if what is the y-intercept. So the y-intercept is when x equals 0, which would be -1 divided by 2. So y equals -1 divided by 2. For the x-intercept, well, for the x-intercept case, we're going to have y equals 0. So that would require 4x squared plus 3x minus 1 equals 0, and working that out I get x equals 1/4 or x equals -1. And next let's find any local maximums or minimums. So y prime is equal to 8x plus 3 times x plus 2 minus 4x squared plus 3x minus 1, and that whole thing is divided by x plus 2 squared, and it should equal 0 if there's a maximum or a minimum. So that would mean that the top part is equal to 0. So expanding this out, we get 8x squared plus 19x plus 6 minus 4x squared minus 3x plus 1 equals 0. And then simplifying it down, 4x squared plus 16x plus 7 equals 0. And then solving that, we get x equals -1/2 or -7/2. So those are our two values of x where we have a local maximum or a local minimum. Now lastly, let's go ahead and calculate the range of this thing. So finding the range of this thing, is the same technique as we did in the first part of this exercise, which essentially is we're looking for all of the values of y that can have an x sent to them. So essentially we're looking for all of the values of y for which there is an x value for which this whole equation can be defined. So rearranging this equation, we get xy plus 2y equals 4x squared plus 3x minus 1. And then rearranging that, we have 4x squared plus 3 minus y times x plus, minus 1 minus 2y, or minus 1 plus 2y, however you want to think of it. And this should equal 0. Now we're dealing with real numbers here because we're graphing these things in the xy plane, so real number plane. So we need all the values of y for which there is at least one value of x which solves this equation here before there can be an x that is sent to that particular value of y. And in order to get a real number x that solves that equation here, we need the discriminant of that equation to be greater than or equal to 0. The discriminant of this equation clearly is 3 minus y squared minus 4 times 4 times negative 1 plus 2y. So the negatives cancel, and we have 3 minus y squared plus 16 times 1 plus 2y, and we need this thing to be greater than or equal to 0. Now, if that was confusing just then, just think about it like this. Y is some real number, and in order for y to be in the range of this function, there needs to be at least one real number x that can be sent to that real number y. So you can say fix y as a real number. So y is some fixed real number, and you basically want to check if y is in the range. So you want to check if y is in the range. Now, y is in the range if there is at least some value of x that can be, there's at least one value of x that can be sent to it. Or in other words, at least one value of x which makes this equation true. And rearranging this equation, we get this quadratic here. So that real number y is in the range of this function if this quadratic equation has at least one real value of x that satisfies it. And the way to check if there's a real value of x which satisfies a quadratic equation is to check if the discriminant of that quadratic equation is greater than or equal to 0. And so the discriminant is 3 minus y squared plus 16 times 1 plus 2y. And then, if y is such that this discriminant is greater than or equal to 0, then y must be in the range. So that's all we got to do now. We just got to find the values of y which make this thing greater than or equal to 0, which is easy to do. 9 minus 6y plus y squared plus 16 plus 32y needs to be greater than or equal to 0, which is the same as y squared 32 minus 6, that would be 26. So plus 26y plus 25 needs to be greater than or equal to 0, and we can even factorize that. Y plus 25, y plus 1 needs to be greater than or equal to 0, and you can sketch a little parabola. This is your y-axis, this is, I don't know, your z-axis, where z is equal to this function here. And we see it cuts the y-axis at -1 and -25. And then the parabola looks like this. Well, hopefully better than that, but you get the idea. This is the function z equals y plus 25 times y plus 1. And we can see that z is greater than 0, or greater than or equal to 0 for y less than or equal to -25. And z is greater than or equal to 0 for y greater than or equal to -1. And so that is our range. The range is y is less than or equal to -25 and or y greater than or equal to -1. Now, if you recall earlier, we calculated y prime equal to 0, and we found that there is maximums or minimums. Well, we didn't prove that they're maximums or minimums, but it's going to turn out they are. Maximums or minimums when x is equal to -1/2 or -7/2. So max / min when x equals -1/2 or -7/2. And if we put those values into the function y, we can see the values that come out. And you can check that for our function y up here, let's call it r of x, just to make it less confusing. So you can check that for our function r of x up here, we have that r of -7/2 is equal to -25, and r of -1/2 is equal to -1. So we clearly have a local maximum at the point, so local max at the point -7/2, -25, and a local minimum at the point -1/2 and -1. And I guess we are finally ready to draw this thing now. Okay, so here's a compiled list of all the useful information and an x and y axes. So let's go ahead and get to work on this thing. So first of all, let's mark out the intercepts. So we have an intercept at -1 and x equals 1/4. And we have a y-intercept at -1/2. Better make that a bit higher up. Okay, and we have a local minimum at -1/2 and -1. So that's like here. So it's -1/2. -1, just labeling that point there, and we have a local maximum at -3.5 and -25. So this can be -3.5 and -25 can be like down here. So I guess about here. -3.5, -25. And we have the vertical asymptote at x equals -2. Can be here. So always draw a dotted line for your asymptotes. And then we also have an oblique asymptote, y equals 4x minus 5. So let's make this -5 here, and it should cut the x-axis at 1 1/4, so like here. So that's our oblique asymptote. Just draw a dotted line for that. I guess I should have calculated where they're going to intercept, where the two asymptotes are going to intercept. And in fact, my gradient clearly looks kind of wrong there, so let me adjust that. So the two asymptotes will intercept when x equals -2. So it'll be -8 minus 5, so -13. So let's say they intercept about here, which means my drawing is not the best, but as long as we got the key points marked. And then just to make it clear that I know my sketch isn't that great, I'll label this as 1 1/4. So 1.25. Oh, by the way, I should label the asymptote with the actual equation of it. So that is y equals 4x minus 5. And just to be clear, we can also call this one x equals -2, just to show the person marking your exam that, yeah, you really do know what you're doing. And then from here, everything is great. I guess I should have called this -25. We are ready to draw our curve. So, well, we know that for x bigger than -2, we're going to have something positive on the bottom and something positive on the top, it looks like, yeah. Well, I mean, since we have x-intercepts at -1 and 1/4, it's basically forced to have this shape here, where it comes up and then cuts the x-axis, and then it's going to go through its minimum point down here. It's going to cut the y-axis at, oh dear, let me try that again. Go through its minimum point down here. It's going to cut the y-axis at -1/2, and then it's going to go through the x-axis again at 1/4. Wow, my scale is too bad. Let me try and salvage this. I guess I'm going to have to cut the y-axis at a slightly... You know what, I think I'm going to have to move my point up a little bit. Move my minimum point up a little bit, otherwise I can't make it work. How embarrassing. Let's bring that up to about there, and then I think I can salvage it. Alright, let's try that again. Because I gotta make it come towards the oblique asymptote as well. That was the problem I was having. Alright, there we go. And so, yeah, because there's only one minimum and maximum, or one local minimum, one local maximum, the curve cannot do things like this. This rational function is continuous as long as x does not equal -2, which means we can draw it without taking our pen off the page at all values of x except for x equals -2. So that means that if there are only two local maximums or local minimums, there should be no other point where it does, no other power where it does something like that, except for at the local max and the local min. We'll talk a little bit more about continuous, what continuous functions mean later. And then all that's left to do is finish off our graph. So something like that. And then just have it get closer and closer to the vertical asymptote x equals -2. So yeah, that should get the marks. Observe that the range of our function is exactly as it should be. The only y values for I guess I should clearly I made this point slightly too high, but that's okay. This is just a sketch, it's not an exact thing. Anyway, clearly the range of our function is as it should be. These are the values of y where we actually have an x value that's sent to them. And let me just continue this axis down a bit. And clearly for y less than -25, we also have x values sent to it. But between -1 and negative 25, there are no x values sent there. So that's true to the range that we calculated.